Everybody, I'm back with another video, and this time we're going to talk about something called the zeros or the roots of a polynomial. They're both called the same thing. They're also called x-intercepts. So just keep in mind that the roots is the same thing as the zeros, is the same thing as the x-intercepts. All right, intercept. All these three terms mean the exact same thing. So when they ask you for the zeros of a polynomial or the roots of a polynomial, they're asking for the same thing. Okay, there's some theorems named after them, like the rational roots theorem, also called the rational zeros theorem. So just keep that in mind, right, guys? All right. So the roots of a polynomial are very important because it's like a way to factor out polynomials. When you can factor out a polynomial, you're actually getting the zeros of it, its roots. But before we get started, I want to draw your attention to this rule I have on the right, the zero product property. So if you have two numbers, a times b equaling 0, then either a is 0 or b is 0 or both of them are 0, right? For example, if you have 5 times 0, well, that's just 0, right? If you have 0 times 7, that's just 0. And if you have 0 times 0, well, that's also just 0, right? So I want you guys to pay attention to that because we're going to use this property to solve for the zeros of this function. So in order to solve for the zeros of this function, what you have to do first is set the function equal to 0. So I'm going to say f of x is 0. So I'm going to say 0 equals 2 times the quantity x minus 1 times the quantity x plus 2 times the quantity x minus 3. But mister, I see 1, 2, 3, 4 terms in this, and your rule only has 2 terms. The zero product property can have as many terms as you want, right? It can be 3 of them. For the example of 5 times 5 times 5 times 0. I don't need to know what 5 times 5 times 5 times 5 is. Because when you're multiplying by 0, the whole thing becomes 0. We don't need to know any of that. All right? You don't even need to know, like here's another example, right? You don't need to know that, go away. We don't need to know that 3 squared times the square root of 25 times the log of, 4 times 0. Oh man, I'm going to solve 3 squared. No, we don't need to do all that. We don't need any of that. Because this 0 right here, it makes things easy for us because it makes the whole thing equal 0. We don't even need to do any of the other math, okay? So just keep that in mind. All right, let's get started. Using this fact, let's solve for this polynomial. So the way you do it is I'm going to grab each term and I'm going to set it equal to 0. Because if one of these is equal to 0, then the whole thing becomes 0. 2, we can leave alone because, well, 2 is not 0. We can't make that be 0. But the rest of them we can because they're variables. So I'm going to grab the first one, x minus 1, and I'm going to set that equal to 0. Next, I'm going to grab the next one. All right, I'm going to put it right here, x plus 2, and I'm going to set that equal to 0. And the last one, let's go with red. Yeah. X minus 3, and I must set that equal to 0. So from here, we can find what the zeros of the function are. In other words, what values give of x give me 0. Right? If one of them is 0, the whole thing becomes 0. So let's see. Well, we have x plus 1, so I'm going to, x minus 1, so I'm going to add 1 to both sides. And my first 0 is at x equals 1. If I plug in 1 in here, the whole thing collapses to become 0. What about this one? We're adding 2, so I'm going to subtract 2 instead. So for this one, I get x is equal to negative 2. There's another 0. If I plug in negative 2 into this function right here, the whole thing collapses to become 0. And the last one, minus 3, so I'm going to add 3 to both sides. So I get x is equal to positive 3. And these are my zeros right here. These are my zeros. So my zeros, or roots, right? You can also call them roots. You know, that's the title. I call the roots. But in parentheses I have zeros. So the roots are, well, the whole thing becomes 0. So y is 0. So in coordinate form, the roots are, for the first one, it's 1, 0. For the next one, it's negative 2, 0. And for the last one, it's positive 3. My mistake. Positive 3, 0. And what does that look like in the function? Remember our zeros, okay? 1, negative 2, 3. And I actually have a graph for us right here. So this is the same function that we solved. We look here. There's 1, 0 there. There's 1, 0 there. And there's 1, 0 there. Negative 2, 1, 3, which is what we have. Negative 2, 1, 3. Not in the same order, but it doesn't matter. Okay? So we use the zero product property to solve for the zeros of this function. And the way you do it is you grab every term that can be 0 and you make it 0. The 2 we didn't touch because 2 is 2, right? It's not a variable, it's a constant. So you leave it alone. So let's solve another one. Keep this in mind. Put in your notebook if you need to, but I'm going to keep using the zero product property. Here's another example. All right, here we go. I have for us the following one. All right, here we go. I have this. So number 2. Negative 2. Well, let me give you the function. So we have f of x is equal to negative 2 times the quantity 3n minus 1 times the quantity, oh, I'm sorry, I use x as my term. Sorry. My notes have a different variable, but I'm going to keep it x. 3x minus 1 times the quantity 2x plus 1. Just like that. So we need to find the roots. Alright, so let's find the roots. So we're going to grab the first one right here. This one right there. That's our first variable term that we can set equal to 0. So I underlined it in green, so I'm going to set equal to 0. Here we go. So 3x minus 1 is equal to 0. Alright, to find the roots, all you do is set it equal to 0. And the next one, let's go with an easier color. We're going to go with blue right there. So now I'm going to set this one equal to 0. So 2x plus 1 is equal to 0. Alright? So let's solve the first one. I have a plus 1 or minus 1, so I'm going to add a 1 to both sides, just like that. Okay? So now I have 3x is equal to 1. I divide by 3 to get rid of it. So x is equal to 1/3. So that's my first 0. My first 0 is 1/3, comma 0. What this format is the coordinates. Okay, so this is the coordinates for my 0. Let's solve the next one. So 2x plus 1. So subtract 1 from both sides. I have 2x is equal to negative 1. I divide by 2 on both sides. That goes away. So I have x is equal to negative 1/2. So my second root is at negative 1/2, 0. And these are my roots right here. Alright, these are my roots. Let's check on the graph. I have prepared it for you guys. So 1/3, 0, and negative 1/2, 0. Let's see what I got. Take that one off, and here we go. So I'm going to zoom in here. Negative 1/2, 0. 0.5, negative 0.5 is the same thing as negative 1/2. And here we have 0.333333 repeating, which is the same as 1/3, 0. So our format our calculation is correct. Okay? So let's do another example now. All right, we're good so far. Just remember, set them both equal to 0 and the whole function collapses to 0. All right? It's a very good use of the zero product property. Here I have another example for us. This time it's going to include a little bit of manipulation. All right? So our third example is the following equation. X to the 4th power minus 16. All right? Oh, I forgot to write it as a function notation. I apologize. So f of x is equal to x to the 4th power minus 16. All right? So far, so good. I'm going to do a little trick here to help me break this one down, because a polynomial will have as many roots as the degree of the polynomial. So this one right here on the previous video I uploaded, this is a degree 4, which means that we have 4 zeros. All right? We don't know if they're real or if they're imaginary, but it does have 4 zeros. So we need to find 4 zeros. If we look at the previous examples we did, this is a second degree because our x times x, it'll be a second degree, so it's 2 zeros. This is a third degree, 1, 2, 3, then we have 3 zeros. Okay? Sometimes they're real, sometimes they're not. What I mean by that is sometimes they'll appear on the graph and sometimes they won't. We'll go over what imaginary numbers are later. But this is degree 4, so I'm looking for 4 zeros, 4 roots. All right? So let's see if we can find them. I need to factor this out. This is a difference of perfect squares, because let me rewrite this. X to the 4th is the same thing as saying x squared minus 16, which is the same thing as saying 4 squared. So this is a difference, subtraction, a difference of perfect squares, which means I can rewrite this now as x squared plus 4 times x squared minus 4. This is a technique you can use to factor out a polynomial very easily. In this case, it's a degree 4 and the perfect square, so we can break it up. But mister, look, you have a 2 and a 4, another set of perfect squares. Good catch, good catch. Another difference of perfect squares. So let me break that up now. I'm going to break the first one, I'm going to leave alone. X squared plus 4. And now I'm going to break this one up further. All right, this one right here. So x squared minus 4 is the same thing as saying x squared minus 2 squared. So I'm going to grab one x here and another one here. And because it's a difference, that means they have opposite signs. So plus and minus. And because this is a 2, we put a 2 here and a 2 there. Just like that. Easy peasy, lemon squeezy. Alright? So now we can set these equal to 0 to find our roots. I'm going to go with this one first. Alright? So we have x plus 2 is equal to 0. We subtract 2. We get x equals negative 2. So our roots will be over here. Roots. We have the first root that I calculated is minus 2, 0. Alright? I'll keep it in green so you guys can better keep track of it. So minus 2, 0. That's our first root. Alright, we're done with that one. Let's do this one now. Set it equal to 0. Add 2 to both sides. We get x is equal to 2. So our second root is 2, 0. Boom. We have 2 roots now. Now we have to find the last two, because remember, degree 4 means we have 4 roots. We have 2 roots. Now we gotta find a way to make this equal to 0. So we have x squared plus 4 is equal to 0. Here where we're gonna run into a problem, because there's no numbers in the real system that give us 0. However, we have imaginary numbers that we can work with, lateral numbers that we can use to help us solve it. So I'm going to treat it just like any other algebraic equation. So we have x squared is equal to negative 4. And a lot of you know how to get rid of an x squared. We use square root. So now I'm going to take the square root of both sides, okay? So square root, square root. The square root of x is just x. And the square root of negative 4 is plus or minus 2i. Just like that. So our third root is 2i 0. And our fourth root is negative 2i 0. And these are our 4 roots. Let's graph it, and then you'll only be able to see the first 2. The third and fourth root are not visible because they're in a different realm of numbers, right? Think of it as a different dimension, but they are real, even though if they're called imaginary numbers. It just goes back to history. It's a very funny history, right? So let's graph x to the 4th power minus 16, and you'll see this green and blue root only. So let's get rid of that. So here we have x to the 4th minus 16. Let's zoom out. There it is. It's a very big one. There's one root right there, and there's one root right there. It is 4th degree, so there are 4 roots, but only 2 of them are visible in the real number system. So minus 2, 0, and 2, 0. The other 2 roots are hidden. All right, they're not visually there, but they are numerically there. So minus 2, 0, 2, 0, compared to what we have. There it is. Cool. So just because they're not there doesn't mean they don't exist. All right, let's do another example. All right, remember, just set them equal to 0 and you find the roots. 0 product property. What example are we on now? Example number 4. Here we go, example number 4. I have this one for you guys. I have f of x is equal to x times x squared minus 2x minus 8. All right, awesome. Before we find the roots or zeros, we're going to do this with factoring, okay? So let's break down this bad boy right here. All right, I can tell right now just by looking at it we can factor. So factors of 8 to get specifically negative 8, right? This is a negative symbol right there. To get negative 8, we have negative 8 times 1, or 8 times negative 1, or negative 4 times 2, or 4 times negative 2. These are the only ways to make 8. So it's either this one, this one, this one, or this one. These combination of factors give me 8. But we have to consider which combination of factors, when we add them, give me negative 2. So let's try the first combination of factors. Negative 8 plus 1 gives me negative 7. It does not give me negative 2, so we can't use that one. So this is not it. Let's try the next one. 8 plus negative 1, well, that's just 7. Again, that doesn't work. So it's not that combination. There's not this combination of factors. Let's try the next one. Negative 4 plus 2 give me negative 2. Hey, that gave me -2 right there. So this is it right there. If you want, I'll check the last one. Watch what you get though. For adding a negative is the same thing as subtracting. I get +2. But right here, I need a -2, which means that our factors are going to be these two right here. Because they multiply to give me -8, and they add to give me -2, which is what we need, a -8 and a -2. All right, so let's use that. We're going to use these factors right here. All right, let's use those. So let's factor this bad boy out now. I have x times two binomials. The first one is going to be x in the front, and it's going to be -4 plus 2. In a previous video I did, if you FOIL this out, you will get back the trinomial on top. First, x squared. Outer, right? Let me just do it quickly. 2x. Inner, -4x. Last, -8. Break it down further. Combine like terms. And look at that. We get it back. Pretty cool. All right. So now we have 3 roots, right? Because we have 3 terms. 1, 2, 3. So we need 3 roots. So let's find the first one. What value of x makes the whole thing collapse? I'm looking at this x first right there, that one. Which value of x makes it collapse? Well, according to the zero product property, if this x is 0, the whole thing becomes 0. So that's our first root. So the roots. The first one is 0, 0, right? X equals 0. Because if we make x 0, because this one's being multiplied, the whole thing collapses. Let's look at the next one now. X minus 4 is equal to 0. I add 4 to both sides. I get x is equal to 4. There's my next root. 4, 0. Now let's get the last root. X plus 2 is equal to 0. Minus 2 minus 2. The third root is -2, 0. And these are our 3 roots. Let's graph it to make sure everything's okay. And I'm going to graph the original one to make sure I made no mistakes. So x times the quantity, x squared minus 2x minus 8. Here we go. Let's graph it. So x times x squared minus 2x minus 8. And here we have our 3 roots. We can see them. 1, 1, 2, 3. Look at that. -2, 0, 0, 0, 4, 0. Exactly what I have. Awesome. All right. Let's keep going. Let's do another example. All right. I have this one for you guys. This one's a little tough, but we're tough people. I have, ooh, this was cute. All right, I have this one. F of x is equal to 4x times a quantity t minus 2 squared times a quantity t plus 1. Oh, I'm sorry. My notes have t's and I'm putting t's here. Sorry about that, guys. X. The reason I'm using x is because that's how it's entered in Desmos. So, apologies for that. Now, how many roots do you guys suspect we're going to have? Well, we have a degree 2, so that's 2 roots. We have a degree 1, so that's 3, right? And then this one right here. So, we should have 4 roots. All right? We need 4 roots, 4 zeros. Let's expand this a bit so we can better see it. For x, and x minus 2 quantity squared is the same thing as saying x minus 2 times x minus 2, and then x plus 1. All right, so now let's set every single one of these equal to 0. Let me pick a different color for all of them. So I have 4x, then I have x minus 2, then I have x minus 2 again, then I have x plus 1. There we go. So four different colors, 4 different roots. Let's start with the first one. 4x is equal to 0. Well, we divide by 4. Our first root is x equals 0. So that's one root right there. So number 1. Let me just put them in coordinate form. 0, 0. When you have a term by itself, just out here like this one, and the previous example, the polynomial has a root at origin. 0, 0 is origin, if you guys remember that. So the next root we're dealing with now is x minus 2, set it equal to 0. Add 2 to both sides. X is equal to 2. There's my next root. 2, comma 0. Excellent so far. The next root we have is again x minus 2. Right? Add 2 to both sides. X is equal to 2. So we have another root that's the same as 2, 0. So when this happens, right here, when you have 2 roots that are the same, we have a double root. So here we have a double root. So what that means is, I'll show you graphically what that means. It's a little, when you have a double root, it is a little different than the rest of the roots. They have a very cool feature that they do. But it's still a root. We still have 4 roots. So it just so happens that one of them is a double root, so it counts for 2. So the last root we have, minus 1, minus 1. X is equal to negative 1. So our last root is negative 1, 0. So here we go. 1, 2, 3, 4 roots. And it is a 4th degree polynomial. So we're solid. Let me graph this for you guys so you can see what it looks like with the double root. I want you guys to pay close attention to that, okay? We have a double 0, a double root. So here, let me graph it. 4x times x minus 2 quantity squared times x plus 1. Negative 1, 0. Is that one of them? Right there, negative 1, 0. Good. 0, 0. Yep, origin. And look what the double root does. It's different from the rest of the roots because the double root doesn't cross the x-axis. When you have a double root, it hits the x-axis and then bounces back up. All right? It does hit the axis, but it doesn't cross it like the first 2 roots do. You see that? 1, 2, and this one right here is 3, 4. Double roots hit the axis but bounce back up. All right? They ricochet. The single roots cross it straight up. They go through it. They hit it and they go through it. They intercept it. Right? This one does hit it, but it doesn't go to the realm of negatives. You see, it hits it, becomes 0, and then it bounces back up. It doesn't go negative value like these roots do, right? It starts positive, 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 negative, 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 and then negative to positive, and then it starts going down, positive, positive, 0, and then back to and then positive again. It doesn't cross. It hits it, and then it bounces back up. It ricochets. All right? That's what double roots do. They're they have that feature. They hit it, the x-axis, but then they bounce back up. So they do become 0, but they don't switch signs from positive to negative or negative to positive like these other roots do. Those hit it and they change positive negative or negative to positive. Double roots don't do that. They hit it and then they bounce back up. Let's do another example, guys, and then we'll be done. Last example I have for you. Oh, this is going to be fun. I have the following example. F of x is equal to, let's do this one, 2x to the 4th power minus 8t x cubed plus 6x squared. Alright, before I even start it, my suspicion is I'm going to have 4 roots because it's a 4th degree. Alright, 4 roots. What are those roots? Let's find out. But before I even start, I want everyone to notice that they each have an x. You see that? That means that we can distribute out an x squared term. Not only that, notice that all the numbers are also even, which means that they also share at most a 2. So what I'm going to do is I'm going to take out those terms I mentioned. So they share a 2, x squared. I'm taking it out, okay? And now, how do I get 2x squared to become x to the 4th? Well, I multiply by x squared again, like that. How do I make what times 2x squared gives me 8x squared? Well, minus 4x. If you distribute this, you get these numbers we originally started with back. And how do I make 6x squared become 2x squared become 6x squared? Well, I multiply by 3. Look at that. And now we can break this down even further, right? I'm going to factor out this polynomial right here. So I need numbers that multiply to 3 that also add up to negative 4. Well, it's a positive 3, which means there's only 2 possible combinations. 3 times 1, because 3 is a prime number, or negative 3 times negative 1. Right? Because a negative times a negative is a positive, and a positive times a positive is a positive. So now I have to look at which numbers can I add to give me negative 4. Well, 3 plus 1 is equal to 4, not negative 4. So it's not that, which means it's going to be the second pair of numbers we have. And here it is to verify. Look at that. So these are going to be our factors right there. So let's use that. So I have 2x squared, 2 sets of parentheses because we're factoring it out into a binomial. This trinomial is becoming 2 binomials. X and minus 3 minus 1, just like that. Awesome. Now we can find our roots. So let's set the first one equal to 0. So 2x squared is equal to 0. Wait, it's a square, which means we have two of them right there. We divide by 2. Let me move it up a bit. We get x squared is equal to 0. Take the square root of both sides. X is equal to 0. So that's our first root. But remember, it was a second degree one, which means that this is going to be a double root. 0, 0, and another 0, 0 root. Right? I'm writing it twice so that we can keep track of the number of roots we have. So right here we have a double root. This is right here is a double root. which is why I have 2. Let's head over this one now. X minus 3 is equal to 0. Add 3 to both sides. You get x is equal to 3. There's our third root, 3, 0. And our fourth root, let's go with orange, right there. X minus 1 is equal to 0. Add 1 to both sides. X is equal to 1, which means our fourth root is 1, 0. So I suspect that at 0, 0, it'll ricochet. It'll hit it and then bounce back up or down, depending if it's opening up or downward, all right? Or which direction it's coming in. So let's graph our original function and let's confirm our roots. And then that'll be all for today. So 2x to the 4th power, here we go. 2x to the 4th power minus 8x to the 3rd power plus 6x to the 2nd power. And there's our double root, just like we suspected. It hits it and bounces back up. So that's 1, 2, 3, 1, 0, 4, 3, 0. Let's check our answer. 0, 0, 1, 0, 3, 0. 0, 0, 1, 0, 3, 0. Voila. Absolute cinema. I hope this clears things up, everybody, on how to find zeros or roots. Remember, they're both the same thing. Also called the x-intercepts, right? They have 3 names. This is a good way to determine behavior of graphs and to get possible graphs, right? When you're given this, you can say, oh, cool, I can graph it, and now I know what the possible function could be, right? You got to play around with it. But this is how you find the roots. Set them equal to 0, and don't forget the feature that double roots do. So we do have 4 roots, right? But our graph shows 3, but one of them is a double root. So 1, 2, 3, 4. I hope this helps you guys up, and I hope it clears a lot of it. Don't forget to leave a comment, like, subscribe. Let me know if anything needs more clarity, and I'll be happy to do so. Thanks a lot, guys. Peace.